Hello, good afternoon. Welcome to our Ezra Roundtable System Seminar Series. So I know we have people coming from all the different backgrounds all across the campus. But looking at today's topic, actually this reminded me, if I may ask you, what do you think system engineering is about? We all learn physics and chemistry, right? They're about energy and how the elements, how they react and having new things produced. But what is system engineering? So the system engineering, to many people, it's about information and incentives. So that's why I'm so excited about today's talk. So actually today we have Professor Manxi Wu, and she's currently an assistant professor with our own School of Operating Research and Information Engineering here, right in this building. So actually, Manxi, she did her PhD study at IDSS, I think, Institute of Data Science.
Data System Society.
Yeah, Data Science and System Society. Yeah. So and also and then after that, actually, she at MIT, and after that, and then she moved to the West Coast to spend some time with the Simon Institute, Simon program, and also as a research fellow and also a postdoc there. And her work has been exactly focused on information and incentives being applied to many, many interesting and complex systems. So, Manxi, I will leave it to you. Thank you.
Thank you very much, Oliver. Okay, thank you guys for being here. I really appreciate that. So I'm going to talk about information and incentive design in congested network. Please feel free to stop me and ask the questions if you have any. Okay, so I think urban systems is in an exciting era where the new technologies basically are mainly powered by all the sensors and communication infrastructures that are embedded into our infrastructure systems that are able to collect massive amounts of data, doing predictive analytics, and sending the information and organize new markets, for example, the navigation systems, as well as the ride-hail services. And there are new ways of conducting the mobility services with, for example, the electric vehicles as well as the autonomous driving vehicles. And these information and incentive mechanisms are changing the way that people share the infrastructure capacity. Particularly, I want to emphasize that these services both change the information environment. That means how the way that people receive information and processing them, as well as the incentive. Our people are incentivized to depart at this time and which route they're going to use. So although congestion games or congested networks is a classical topic that in the complete information environment, we know most of the results and they're pretty complete, but these new technologies actually create new models as well as both theoretical and empirical works that are worthy of study. And second is there are often different trade-offs between different types of objectives. Okay, so the outline of today's talk is that I'm going to first talk about the topic of information design. I'm going to look into how the platforms can leverage information asymmetry in order to affect the strategic behavior of agents in a congested network market to maximize their revenue. In the second part of the work, I'm going to show a modeling plus empirical work to look into how incentive design, particularly is this dynamic tolling in high occupancy toll lanes, are going to promote carpooling on a highway in California. Okay, let's jump right in. The first work, this is the title, and this is joint work with Professor Ozan Pendogan from Chicago. This is motivated by the fact that in many operations management settings, resources, here this means, for example, the delivery person, as well as the Uber drivers, as well as the jobs, the requests of services are spatially distributed, and there is often mismatch that causes the inefficiency of this market. For example, you could imagine if most of the demand distributes in the center of the city, however, most of the drivers are clustered on the highway near here, then the waiting time of the passengers is going to be very high in the system, and platform revenue will also drop. Well, this issue is further complicated because these resources, which are the service providers, are self-interested, they are independent contractors, and they're going to decide strategically about where they want to position based on their knowledge as well as the information provided by the platforms about how the demand is distributed. These platforms right now, they're providing a heat map to demonstrate the distribution of the demand in the network, and drivers are going to use this heat map to draw a demand estimate about how the demand is distributed, and then based on their current location, they're going to make a strategic decision about where they want to position themselves. This will change the prices of different locations as well as collectively the total revenue of the system. The question is, first, how should the platforms leverage their information advantage to influence the decisions of self-interested contractors and to improve the revenue? And second is, what types of information structures are practically relevant? The main contributions of this work is, first is that we formulate a game-theoretic model to capture the information of the shock that on the contractor's spatial repositioning strategies. And second is that we look at the second question, which is equally as important as the first one about maximizing revenue, because human brains are not functioning in a way to process very complex and random information structure. Particularly, we want to show that in many practically relevant settings, a very simple information structure called monotone partitional information mechanism turns out to be optimal. And what do I mean by a monotone information mechanism? For example, here, the heat map is a monotone partitional. The shock strength from the low demand to high demand is partitioned consecutively and marked with different levels. Basically, when you see this color, you will know that the demand is higher than a particular threshold. And when you see this one, you know that it is in the middle, within an interval. What is not a monotone partitional information structure? First one is that the signal is actually randomizedly generated. So when the demand realization is here, I could either receive a high demand alert or a low demand alert. This is undesirable and quite confusing for the drivers, and this may cause some mistrust for the system. And second is that although it is deterministic and partitional, but this is not monotone. This kind of information structure also creates confusion for the drivers to draw a reliable estimate about the environment. The third is that we design efficient algorithms for computing the optimal as well as near optimal information mechanism. Okay, I'm going to be very brief on the related literature. Essentially, it's related to the early development of information design in economics, the information mechanism in traffic routing, as well as revenue management. The emphasis of our work is that first we look into a spatial setting, and second is that our main focus is the optimality of this simple information mechanism. Okay, so here is the model. I consider a network with nodes, and each node is initially endowed with a group of drivers that has size mi, and the drivers are deciding the cost of repositioning as their distances between two nodes. Well, the repositioning strategy is basically for drivers that currently at each node I, they are going to decide whether or not they want to go to another node j, and this should sum up to the original mass. The redistribution of the agents will create a distribution of drivers after their reposition. And how does it affect the revenue as well as the price? We assume that the service price at each location I is a decreasing function, where Si represents the average volume of this market, and beta I estimates the elasticity of drivers in this market. This can generalize to piecewise linear function, but I will not talk about this generalization in this talk. The initial distribution is Mi. After people reposition, it leads to Qi, and then the price changes. The realized price of the market is after the reposition, and the platform is going to take a particular proportion as the commission rate of this revenue. So the platform's profit is to maximize the total revenue collected from this condition in all the nodes of this market. Shock will affect the market sizes, which means that it's going to move this linear price curve either upward when there are higher demand. So given the same amount of service providers, the price is going to be higher in this market. Or it could be lower if there is a reduced demand. The state of the network is basically this distribution of SI nodes. Okay. So the information mechanism maps from the state to a signal space, and the platform will choose this information mechanism before observing the state and generate the signal according to this distribution. Agents have the prior knowledge about the distribution but do not observe the realized demand. So for example, if there are frequent drivers, they know roughly how the demand is distributed in the network, but they don't know the particular realization of that thing. Based on the signal, they are going to estimate a posterior mean of the demand of that location and then make a repositioning strategy based on the information that they receive. Okay? So basically, if agents and location I decides to move to location J, which means in equilibrium there is a positive volume of agents moving in this direction, then it means that moving to J actually maximizes the utility. It is a better choice, or it is a choice that is not worse than moving to any other location or staying at location I in this network. And here it incorporates the estimate about the demand and also deduct the cost of repositioning. Okay, so let's take a look at how the model works. The platform first selects an information mechanism that translates from the demand information that they observe, the demand state that they observe, to a signal. Then the state realized, and then the signal is generated. The agents will then observe the signal to update their belief about the demand distribution, obtain an estimate, a posterior estimate about the demand, and then agents will reposition. And platform will collect revenue according to the equilibrated market outcome, according to a ratio. The platform's problem is to design such an information mechanism to optimize the total revenue in a whole network. That includes, first is this revenue function for any realized demand as well as the realized signal. This needs to incorporate the strategic reposition of the agent's behavior in the network. And then we take expectation over both the signal as well as the state space. Both the signal as well as the state space could be continuous, so I'm taking the integration here. There are three main challenges of solving this optimization problem. First is that equilibrium characterization in this network is really daunting. It's not a simple optimization, but there is an equilibrium strategy profile that is embedded in the objective function. Second is that information design is inherently an infinite dimension optimization problem because both the state and the signal can be continuous. The third is that this optimization problem itself doesn't really tell us what are the conditions where simple partitional mechanism is optimal. So our approach of tackling the first problem is that we go back to the title. This is a congested market, so it is a congestion game, and we can actually write a slightly revised potential function to solve the equilibrium for any given realized signal. So this allows us to compute the equilibrium given a single signal realization as a convex optimization problem, and this solution is unique, which means the platform doesn't face a problem of equilibrium selection. This allows us to reformulate the revenue optimization problem as to find a posterior mean distribution G rather than looking into the original signal, such that it maximizes the expected distribution of the revenue given a realized posterior mean. From Blackwell's theorem, we know that such a G can be induced from a prior if and only if the prior is a mean preserving spread of the G distribution. We further look into a more simplified case. we look at a single shock, and we look at homogeneously balanced market, which means before the shock, the prices at nodes are equal, so agents have no incentive to move around. I'm going to relax the second assumption later in this part. So in this simple case, it's very simple. When there is a positive shock, then agents will move from a subset of nodes to the node where the shock happens, according to a shortest path tree. When there is a negative shock, agents will leave the area that is affected by the shock, and then they're going to move away from that node, also according to a shortest path tree. Under these two assumptions, we actually can show that the revenue function is a piecewise linear function in the posterior mean that agents are going to estimate about the demand realization of the place where the shock happens. This allows us to further write this optimization problem in a simple way, where both G and F are distribution of a single real number representing the demand level at the shock center, and F is a mean preserving spread of G. Okay, so I haven't told you how we're going to look at, yes.
So this ordering that you showed, it's convex ordering between G and F.
Oh?
The ordering that you have between G and F
Here.
is convex.
Is a convex ordering. So if you write it out, it's the integration of G from the lower bound to S is smaller or equal to integration of F. I don't think this is a convex because I'm saying, so the integration is convex, but I'm minusing the two. Yeah, not necessary. Thank you. Any other question? Okay. Any other question about the setup of the model? Cool. Okay, so let's look at three cases. The first case is that the market sizes are actually similar to each other relative to their distances. What does that mean? It means that the intercepts of the price curve of node I and J for any pair of ij divided by their distances. So this evaluates how the market sizes are changing in relationship to their location distances. If this number is smaller or equal to 1 over 1 minus the commission rate, which means that the absolute value of how market density changes in spatially is not too high in comparison to the commission rate, the effective commission rate. Then in this case, we say market sizes are similar relative to distances. We can also define a situation when actually market size decreases faster than you move away from the shock center. So this means that the relative change of this market sizes in comparison to the distance is smaller, is a negative value and smaller than 1 over 1 minus r. The last one is that the market sizes actually increases. So the location where the shock happens, as you move away from it, the market sizes actually increases and market becomes denser. And this is also in comparison to 1 over 1 minus r. Okay, so we show that in the three cases, the optimal information structure is actually very simple. The first is that full information provision, which means you just tell the drivers the exact information about the nodes, is an optimal information mechanism when all the market sizes at all nodes are similar to one another relative to the distances. And empirically, we actually tested that in Manhattan, it falls under this case. So Manhattan, all the different zones of the taxis, they have sort of different market sizes, but their difference is relatively small in comparison to their distances. It's more of a uniformly distributed market sizes. Then we show that in this case, the market sizes, the full information is indeed optimal for maximizing the platform's revenue. Well, in the cases when the market sizes are monotonically increasing or decreasing, in both cases, the reveal, fully revealing the information below a threshold and fully revealing the information above a certain threshold, and put all the states in the middle. So basically, this is like sending alerts when the demand is extremely low or the demand is sufficiently high. And in the middle, you say this is a nominal situation and I don't send any alerts. This kind of information mechanism is in fact optimal in both the monotonically increasing versus decreasing market. This means what? This means that when shock happens in a central business district where the market size is significantly larger than a nearby neighborhood, then you should actually adopt this reveal pull and reveal information structure. This actually holds for the airport area in most of the cities. The last one is when shock happens at a remote area, and a similar information structure is also optimal, but with the posterior mean of the middle regime shifted aside. I'm going to skip the proof, but essentially this is about finding a convex upper closure of the revenue function and try to see if you can generate a signal that represents the point where the convex upper closure touches the original revenue function. And this can also be computed in linear time with respect to the number of nodes in the network. I have time until 1:10.
Yes.
Okay. Okay. So we also can see that because the thresholds about market sizes being relatively similar or increasing or decreasing is in relationship to the commission rate. So when the commission rate is actually larger than the maximum change of the market sizes in the network, then the first scenario where all market sizes are similar is going to be the case. So then full information is going to be optimal if the commission rate is sufficiently high. So this is very intuitive because agents are going to become less sensitive to the information that platforms provide when the commission rate, the rate of the price service provided to the customer, a large proportion is actually taken by the platform.
Sorry.
Yes.
So from the previous, so this convex upper approximation, why it is upper approximation?
Is what?
Why do you have this upper approximation? Do you have any
intuition about this? So the original one that so this needs to be held for any S. G and Z are CDFs. If I take a dual of it, then the dual value of PS, a dual of it will be PS is larger or equal to, so I have a V as DG as integration of S is my objective. So I actually have a minimization problem where I have S, I have PS, DFS subject to PS larger or equal to VS. So this is the dual. So I'm actually solving the dual on the continuous dimension. So the P is actually the convex upper closure of the closure function. And when it actually touches, this is where the strong duality holds, and I can put a positive probability at nodes that it holds. Okay.
And it's always piecewise linear.
Yes and no. So under the assumption that the price curve is linear, you can solve it as piecewise linear. If it is not, it's not going to be piecewise linear, but you can approximate it as piecewise linear. Yeah. Okay, thank you. Okay. The value of information design also increases when there is more randomness in the shock distribution. Because this ordering actually increases in the physical region. Okay, so I'm going to skip the generalization part. Basically, if it is not piecewise linear, you can actually extrapolate it in this way, and we can also relax the assumption about market homogeneity. We also derived a more theoretical result, which I will not talk in detail here. It is a sufficient condition that you can computationally verify when you get distribution of the shock as well as the market price information, you are able to verify whether or not the revenue function is actually an affine closed function, or if it is not affine closed, can you find instances where you can find an interval such that in this interval, monotone partitional is not optimal. If you pass these two tests, then you can conclude that monotone partitional information mechanism is optimal even beyond the three simple cases that we looked into. Okay, so computationally, you can compute the generated signal as well as probability of those signals according to a convex optimization problem with the discretization. And this here, the P is actually the probability of generating a signal that lies in the case interval of the piecewise linear function. And also Kx over Pz is the posterior mean of that signal. With this information, we are able to reconstruct what is the monotone partitional structure given the optimal solution that we have. And this is an optimal solution if and only if for all the non-degenerate intervals, this inequality constraint is actually typed, is equal. So this also provides a computational way to verify this condition. If it is not, then this means that we are going to generate a signal structure where we pull a low and a high state together, where the middle one is left with another signal. And an optimal information mechanism has to have this structure. In this way, however, we're able to reordering these probability pieces to still reconstruct a monotone partitional information structure, and we are able to bound the gap between the two revenues, leveraging how much this the slackness of this constraint at the optimal solution. Okay, yeah.
So this R that you have.
Yes.
So you show it for linear function.
I showed it for piecewise linear. So K is a case piece.
I see. So, but is it possible to just extend it to general convex?
this
Because it still remains fine.
Okay, so the problem is that the objective function when plugged in the equilibrium is usually not even a continuous function. Yeah, so in a lot of cases, like for example, if it's a product, when a product value is low, you buy. When the product value is higher than a threshold, lower than a threshold, you don't buy. Then there's a jump. So usually this R function in information design has a very bad shape, but it can always be approximated by a piecewise linear function. And in our case, this is not guaranteed to be convex unless it falls in the first case of full information provision is optimal. Actually, if this is convex, then full information is always optimal. Yeah. Okay, so let me summarize the first part. Spatial market frictions are very common, and information can be used as a lever to influencing the behavior. The work provides a modeling theory and computational method in the application of the red hat as well as these spatial markets to look at how to design a simple and yet effective information mechanism. Okay, the paper is online. Let's go to the second half. So the first half, you don't charge a certain price to these service providers. You simply just leverage the randomness in the system and decide to provide a partial information about the randomness realization and to incentivize a certain behavior. The second half is probably something we're all more familiar about, is to directly charge a price for using the capacity of the infrastructure at a particular location at a particular time. There is a long history of tolling. This is a picture, I think, the first formal toll booth in Pennsylvania, in the United States. And this is the few later generations of easy pass and the more smarter ways of having the digital boards that are able to charge a particular stretch of the highway with a dynamic price and also account for the occupancy level of the drivers of this vehicle. And lastly, this is the diagram of how Singapore is doing the tolling. they are using this satellite-based tolling, which basically you have an onboard unit that is installed on your vehicle, and this allows for real-time adjustment of the prices as well as non-linear pricing that is not necessarily just based on each segment, but the whole trajectory that you are taking a particular zone. So toll infrastructure are becoming cheaper to implement, more scalable, and this gives us more leverage about how we're able to avoid the traffic slowdown using this pricing mechanism. There is also rich literature on toll design that includes the classical results in static congestion game, the generalized strategic pricing and competition in congested markets, the equity problem in tolling, as well as some empirical study, usually not game-theoretic, but empirical study plus simulation study to look into the lane changing behavior as well as vehicle following in traffic dynamics. The question we still have is how effective is really tolling in practice? And second is that how can we make it better? Well, there were many great works in this space. I want to provide a piece of evidence that me and my co-authors have done in the past 2 years with the database that we collected for the San Francisco Bay Area. With the data that we get from the loop detectors, American community surveys, as well as the phone GPS data sets, we are able to calibrate an entire routing game of the network and compute the equilibrium of this network. The quantity that we care the most is given the equilibrium flow that we observed, and we compute the total travel time of the equilibrium. In comparison to, in hindsight, if people are cooperating and they are routing in a way that minimizes the total congestion, what is the ratio between the two? This is something called price of anarchy for people who are familiar with the classical results in congestion game or game theory in general. And we found that the price of anarchy is a value that is very close to 1. It's actually 1.04. This is not a coincidence. We later found that many empirical studies have found that the price of anarchy is close to 1 in London, in Boston, in New York City. Well, on one hand, this is a good news because it tells us the strategic behavior, the selfish behavior of agents actually do not lead to efficiency deterioration by that much. Because the equilibrium cost, social cost of equilibrium, is pretty close to the social cost of a congestion minimizing flow. On the other hand, this is also a bad news for toll designer because the optimal thing, the best thing you can do through the dynamic tolling is to reach this minimum travel time. So this POA is also a bounds on the maximum efficacy of the tolling, how much improvement you can get. And in here, we can at most improve by 4% in the Bay Area network. This is actually not a coincidence, and it's proved theoretically by this operations research paper, that it shows that in a traffic routing network, when the total demand, so basically the network becomes more and more congested, total demand goes to infinity, it becomes very high, the price of anarchy always goes to 1. This means that in the case that we actually care about congestion the most, when in peak hour of the traffic, it's very likely that this tolling is not going to work. So this is really a bad news, but how can we do better than this? The key is you are going to try to place more people in a single vehicle. This leads to the study of optimal design of high occupancy tolling systems with heterogeneous travelers. And this is joint work with my 2 PhD students, Zhanghao Zhang and Ruifan Yang at Cornell, Oregon. Okay, so high occupancy tollings are expanding in California, and this is all the areas, the zones that it has already been implemented, and they are also constructing a new one. So what you see here is actually a digital board of the fast track. It usually cuts this whole line into segments, and you are charged with a price given where you enter and where you live. And you have dedicated regions near the ramps to enter and leave the high occupancy toll lanes. The charges, usually you pay the full price if you are a solo driver and using that lane. You pay half the price if you are carpooling with one person, and you're free to use that lane if you have more than 3 people in your car. The remaining lanes are open to all the drivers. In order to use this system, you should install something called a fast track flex on your vehicle, and there is a button that you tweak to send signal to the infrastructure. So you communicate with the infrastructure about how many people are there in your car, and your price is adjusted based on it. If this infrastructure does not sense a signal sent from a vehicle that is using that lane, it's going to use the camera to take a picture of the plate of that vehicle, and then you will receive a fine, which is the highest toll price of that period of time, plus $10 or $20, depending on how many violations you have had in your history. Okay, so how to model this? We model this as a game. We have a non-atomic group of demand of travelers going into this lane, and they are going to choose between pay toll price or carpool with a particular size n. So here, for the basic model, we're looking at only a single occupancy level. So you either pay the toll price or you satisfy the occupancy with size n, and it's free to use HOT lane. Or you can use the ordinary lane. And the total capacity of that road is divided between the HOT lane and ordinary lane. The problem is that agents actually have heterogeneous preferences, and this is a latent variable. The system designer, the operator are not able to observe everybody's preferences. They can do a small-sized survey to learn a fraction of their users, but they will not know the continuous distribution. And particularly, people care about 2 things. One is how much value does driving time reduction is for them. So this is the x-axis, we call it value of time. And the y-axis is the carpool disutility, which means if I carpool with someone, how much hassle I kind of experience by that. Given an individual's value of time and carpool disutility, this agent is going to choose a strategy between carpool, not pay, or pay the toll price to use the HOT lane, or use the ordinary lane. And this also depends on the latency, the driving time, as well as the congestion level of each of the lanes. And the congestion level is the aggregate usage from all the agents in the population D who have heterogeneous preferences. Okay? We assume that the cost function of both types of lanes are increasing. So both types of lanes are congested lanes. So an individual with value of time beta and carpool disutility, the cost of taking the ordinary lane is beta multiplied with the driving time cost of the lane O. For paying the toll to take the H lane, it is the cost of the time spent plus the toll price. For carpool, then it is the cost of the driving plus the carpool disutility. And equilibrium is basically saying that for agents with any beta and gamma, their preference parameters, the choice of the action that they are going to take is going to minimize their cost and in the whole set of pull or tow or taking the ordinary lane. And this flow on the high occupancy toll lane versus the ordinary lane are actually the integration of everyone's decisions. And this is according to this probability density function of the 2-dimensional preferences in the 2D space of the parameters. Okay, so how do we characterize the equilibrium? We look at the key quantity called time difference. So this time difference is a value that compares the driving time cost of the 2 lanes. So basically, the design of this HOT lane is to use the time saving, delta, as well as the toll price, T, to screen travelers with different preferences of time and carpool disutility. You could imagine if all the people are taking the HOT lane or a majority of people are taking the HOT lane and delta value is small, then the high occupancy toll lane will become less attractive to the travelers, and then there will be only the ones who have a high preference of the time saving or very low carpool disutility will switch to the HOT lane. Indeed, this provides a way for us to compute the equilibrium in an efficient manner. We start with allocating all the drivers on the ordinary lane, and then we order them according to their disutility of taking the toll lane. So this disutility could be the minimum of the two values. The first value represents paying to take the lane. The second value represents carpool to take this lane. Okay? So with this increasing order, the lower this value is, it means that no matter this person is choose to pay or choose to carpool, the HOT lane will have the most level of attraction for them because they have less disutility of taking that lane. So you start from 0, and then you are going to switch the travelers in increasing order of this value. If for the group of travelers that you are considering right now, their price is smaller than their carpool disutility, then this group of travelers will switch to the HOT lane to pay. Or their carpool disutility is actually lower, then you need to adjust the flow to account for the fact that this group of population are actually going to carpool. Until you are going to arrive at a situation where the minimum disutility of travelers that are still remaining on the ordinary lane has a disutility level that is higher or equal to the cost difference of the two lanes. Okay, this is the algorithm, and I'm going to skip that. It gives us two equilibrium regimes. The first equilibrium regime is when the toll price is relatively low, and actually, given this whole space of value of time and carpool disutility, we're able to truncate them into the three categories. And the category here, basically people who pay to take the HOT lane has either high value of time as well as high carpool disutility. That's why they choose to pay. And we can similarly argue about the two other categories. And this allows us to compute the probability mass as well as the equilibrium flow. However, when the toll price becomes sufficiently high, you could imagine that nobody is going to want to use the toll lane by paying. So then we are left with two categories, ordinary lane or people, whoever take the HOT lane is going to carpool. This actually converts the HOT lane to the classical HOV lane, where you can only take those lanes if you carpool and satisfy a certain level of occupancy, but they actually don't allow you to pay in order to use those lanes. I'm going to be brief on the comparative statics that shows how the HOT capacity as well as the price is changing the proportion of the populations who use each one of the options, and how does it change the priority level of the HOT lane. I just want to mention that here, when you increase the toll price, what will happen? When you increase the toll price, one of the two things could happen. Either your carpool will increase, which means that people will pay less. There will be fewer people who choose to pay, but these people are going to switch more towards forming carpool. This leads to the reduce of emission. So this is a good thing when your toll price increases. It could also lead to a disastrous outcome, is that these people, instead of carpool, they decide to switch to the ordinary lane. So then the ordinary lane becomes more congested, but the average occupancy level actually do not increase. So this can lead to inefficient lane usage and even increase the congestion. So the objective function about the social cost as well as the emission is not a monotone function in the toll price of the HOT lane. Okay, so the key aspect is how are we going to use the data to estimate the preference distribution. So the data that we got from Fast Track includes the driving time of the two lanes. This is something we estimated from PAMS using the loop detector data. And the flow, we also have the lane by lane flow collected from the sensors on this highway. What's provided by the fast track is actually the 5 minutes toll price for the year of 2022 on the highway I-880 near Fremont. So we want to use this information to estimate the distribution of travelers' preference parameters. It is a continuous function, so we are going to discretize it. We are going to set the grids of the value of time and carpool disutility, and within each grid, we assume that it is uniform distribution. But what we care about is how, in each different regions, what's the size of the total population that they are in. So this gives us an estimate about this probability density function, and the finer your grid is, the more accurate you are estimating the preference distribution. So we grid this into K, and then for each small grid, we're going to uniformly sample m numbers of beta and gamma tuples in this set. And we know how equilibrium works, so we are able to assign each one of the individual sample agents to the action that they are going to take in equilibrium, given the driving time as well as the price of the HOT lane. So assuming that they are selfish. And in this case, this allows us to compute the equilibrium distribution for the travelers with uniform preference parameters in each small grid. And this gives us this equilibrium strategy for that small population. Then we are going to compute the sizes of each population in a way such that the aggregate flow matches with the observed flow. So essentially what we are doing is that we want to minimize the equilibrium flow that we compute from the equilibrium on both the HOT lane as well as the ordinary lane. We want to minimize the gap between this equilibrium flow and the flow that we observe. So this is something similar to this inverse optimization approach that people use to look at when I do not know about a parameter of a system, but we assume that people are choosing things according to optimality. How does that noisy information matches with the actual observation? So this allows us to obtain a consistent estimate for the size of each grid under some assumptions like IID distribution. Okay, so I'm going to quickly wrap up. We have 4 objectives: congestion minimization, which is the total time spent, the total travel time minimization, which accounts for the actual time experience, but congestion only accounts for the number of vehicles. So the difference is that here I adjust by the occupancy level. And revenue is an important aspect as well. And the last one is to account for the total welfare property. I'm going to skip it, but essentially we did an empirical study for the highway I-880 near the Fremont area. So this is Union City, this is Fremont, it's on the east bay of the Bay Area. Okay, we picked 3 months, 5 months, from March to August in 2022, and then we used this every 5 minutes data to compute the HOT travel time and ordinary lane travel time. We can see that the HOT lane is actually faster than the ordinary lane by quite a significant amount. Using this calibration, we recover what is the HOV flow and ordinary flow, and what is the demand distribution of all the travelers for each time step of a day. And this is the percentage that we estimated from the graded preferences. And this is what we find, that the equilibrium and the observed flow for single occupancy, 2 people carpool, as well as 3 people carpool are actually very consistent. So this means our estimate of the preferences effectively recover that the equilibrium flow is consistent with the actual flow. And this is what we computed as the optimal toll pricing for each time step given this equilibrium model, and we compared that to the actual toll price that we observed during the day. And this is for each objective, how much improvement. For example, we can reduce the congestion by 25% if we tune up the toll prices during the morning hours. However, for the revenue, we might want to set a lower price to significantly boost the revenue so that more people are actually taking the solo trip so that the toll price is collected rather than carpool so that actually no revenue is going to be collected in that case. Summarize. In the first part of the talk, we look at how platforms are able to leverage the data advantage to incentivize the strategic decisions by revealing partial information. And this here, we need to consider the complexity of the information structure. And what we prefer is to look at practical scenarios where simple monotone partitional structure is effective. Second half of the talk, we look at a data-driven incentive design problem for populations with heterogeneous preferences, particularly in the context of design high occupancy toll links, where the price and time, as well as the carpool or not, are used as a way to screen the entire population based on their sensitivity to the driving time, as well as their disutility of carpool. And I think the last point is really important because we're not able to collect those too many surveys in order to figure out everybody's preferences. But design of this tolling system crucially depends on our knowledge about the preference parameter distribution. And actually, by just looking at the current system and to leverage the stochasticity and randomness in the data, we are able to estimate approximately a preference distribution at the population level by leveraging the game-theoretic model as well as the aggregate data in the network. Thank you very much.
Yeah, we have time for questions.
Yes, please.
So you seem to be punishing pooling because you don't raise as much revenue. It seems to me that what you ought to be doing is encouraging pooling, and then you'd have fewer cars.
Yes, so that's why I think the current objective, like this is the current toll price. This is in between setting a congestion minimizing toll price and also the revenue. If you want to maximize revenue, you should punish pooling. You should encourage people.
Reduce congestion.
You want to reduce congestion. The way to do that is to charge a high price, so that people actually do not pay that, but to carpool. You need to provide incentive for people to carpool. Otherwise, if it is only charging $1 to $2, people are not going to carpool.
Well, I mean, I looked many years ago, looked at the procedures that Los Angeles tried to encourage people to carpool. And basically the only thing that worked was to have fewer parking spaces at the factory of the workplace. You know, it's very difficult. So have you got data that actually shows the increase in carpooling?
I don't have aggregate data for the Bay Area in terms of parking. That's a very good point.
No, in terms of pooling.
The pooling. Oh, I think at least for Berkeley, the carpool is half of the price of the parking that is a solo driver. Yeah, so that is about $50 saved per month for a person.
What proportion of vehicles
Our carpool.
5% or something?
This I do not know. From my observation, not so much. But it's not just about the price. They also have dedicated spots for carpool parking. I think that's actually more important because during, like for example, at noon, it's very difficult to find an on-campus parking slot, even if you are willing to pay. But they also reserve the space for the carpool vehicles. Yeah. I think that's part of an incentive that is pretty difficult to quantify. Yeah. Yes, please.
So, Manxi, for your first study, your objective function was to maximize profitability for TUC. With how would you justify that objective function?
Yeah.
I assume that, so for example, for a given time, the demand, I think it's safe to assume the demand is exogenous.
Demand is not exogenous.
So but I think there might be some elasticity, but my point is that assume that given time there will be this spatially distributed demand, and assuming that all this demand, they all have their fixed ODs. original destinations. And assuming that you're serving this demand include the cost of the drivers, whatever their fuel costs, plus their margin, and then also the TNC's charge. Assume that there is some kind of fair cost for that. So what I'm thinking is that for TNC to maximize its profitability, the best way is to maximize the service rate. But otherwise, when you try to play with all this information mechanism, so when I'm just trying
okay, maybe I can provide some a few comments at this point. So first is that during the morning, like at 9 a.m., most of the trips end at the midtown. There are very few trips that end elsewhere, but trips are going from those peripheral areas to the midtown. So there is an imbalance that requires the vehicle to reposition.
Yes.
So the reposition is not something that platform can control. They need to provide incentive. There are two ways of incentivizing this reposition. Is that when more drivers leave an area where it creates a higher demand than supply, then price for that area will increase. This is from the price curve of the equilibrium model that we look at. And second is that you want to use information because only the platform actually knows how much new demand is generated and where drivers are needed. So this is the goal. This is a methodology that for a piecewise linear function, you are able to computationally verify if this simple mechanism is optimal, or you can use other ways to compute the optimal information mechanism. You can change the revenue function, the objective, into other objectives. Actually, we also tried the driver's welfare, which account for the money, the per hour money that they earn. Then it will give you a slightly different result. We also look at this vehicle utilization rate, which is about you want people to reposition, but you also don't want people to reposition to a long distance location because that percentage of time is the percentage of the fleet that is not being utilized. This is something called wild goose chase and a ride-hailing system. So we also want to minimize that. And interestingly, we found that in Manhattan, providing no information minimizes this empty vehicle routing, and providing full information maximizes the revenue. So depending on the relative weight between the two objectives, you want to try to find a partial information correlation.
Yes, so my question is more, I believe providing information will always help reposition.
Not necessarily.
Providing
information always helps market efficiency. Yes.
But my point is that, so you are talking about different information provision mechanism.
Yes.
And by different information provision mechanism such that the TNC can exploit some profitability. My question is, where does that delta profit come from across these different information mechanisms? It has got to either come from the rider or come from the driver.
It is actually removing the driver and the rider's welfare to the platform's profit. So if you want to maximize the total welfare of the system, you can prove that full information provision is optimal. The first half of the talk was in the revenue management kind of law that looks at how the platform would be interested in leveraging that. And this is actually a topic that Uber is interested in. They want to know how to design this heat map to do this. So
that sounds very dangerous because that could put Uber easily into a case of a cliff.
So actually in Manhattan, full information is their optimal. So in some cases, for example, Manhattan, it seems like the platform's revenue as well as the social welfare are aligned. But in other places, for example, airport, I don't believe that's the case. Airport, it's about sending a partition information. So the first work is joined with a B school professor. It's in the revenue management community. So it's talking about revenue. I totally agree with you. For total welfare, you should provide full information. But actually, when I talked with Peter, taught me a lot of things about this. Uber also cares about driver welfare as well as the vehicle utilization. For vehicle utilization, actually, you shouldn't provide too much information because you don't want the system to fluctuate a lot. The first part is more of a computational framework. We can talk more. I totally agree with you that may not be a good thing to really design information this way. Yeah, thank you.
Any other questions? So in that case, shall we call it? So thank you very much.
Yeah.